When preparing to take precision measurements, it is important to know the accuracy with which the part being measured requires. Parts requiring accuracy within 1/10 of a millimeter may include the brake lining thickness, clutch disc thickness, and the brake disc thickness. Engine parts typically require a greater deal of accuracy when being measured. Some parts must be measured to within 1/100th or 1/1000th of a millimeter, such as piston outer diameter, cylinder bore diameter, and various other engine parts.
Feeler gauges are used to measure clearance. Clearance is the space between two surfaces. Typical applications requiring feeler gauges are oil pump inspection, piston ring land clearance, and valve clearance.
Vernier calipers and digital calipers are used for a variety of measurements, such as thickness, height, inner diameter, and outer diameter.
A dial indicator is used to measure variation and movement. Some typical measurements include runout, end play, and inner diameter. A micrometer is used for measurements requiring great precision. Some of these measurements include thickness and outer diameter. Some precision measurement tools, such as those listed here, require the use of a micrometer to read the value of their measurement.
Few things that can affect the accuracy of a feeler gauge: mechanical wear or damage to the tool, and dirty measuring surfaces or blades. To keep your feeler gauges in good working condition, only remove the blade you want to use from the holder. Wipe the blade clean before and after each measurement. Return the blade to the holder as soon as you finish using it, and store the blades in the folded position in their holder. To check for wear of the gauge blades, measure the blades with a micrometer. You'll learn how to do this in the next section. Replace the feeler gauges if they are found to be excessively worn. Vernier calipers and digital calipers require minimal maintenance to perform properly for several years.
Keep the tool clean and always store it in its case. Do not place heavy objects or other tools on top of the vernier calipers. Dial indicators make precision movements. They require careful handling and storage to maintain integrity and accuracy. To keep a dial indicator working properly, always handle with care. Keep it clean and store it in a way that it will not be damaged by other parts or tools. A micrometer requires careful handling and storage to maintain precision and accuracy. Handle a micrometer with care. Keep it clean and store it in its case so that the spindle is not touching the anvil. Make sure that the spindle lock is applied. The feeler gauge set is made of several thin metal blades, each machined to a specific thickness. Metric sets typically range in thickness from 0.05 of a millimeter to 1 millimeter. Combining blades allows you to measure a clearance for which there is no single blade available. Blades come in various lengths to accommodate different applications. Certain measurements may require special feeler gauge sets, such as angled gauges. It's not actually possible to calibrate feeler gauges. However, they should occasionally be checked for excess wear to make sure they are still in calibration. If you fail to do this check, you could set clearances too tight and cause service problems. This check is done with a micrometer. Micrometers are covered in the Advanced Precision Measurements module. If you don't yet know how to use one, ask another technician to do the check for you. To check a feeler gauge for excess wear, remove the blade from the holder. Make sure it's clean. Note the measurement value on the blade. Then, set a micrometer for that value and apply the spindle lock. Drag the tip of the blade through the opening between the spindle and the anvil. If there's not enough resistance, the blade is excessively worn and will need to be replaced. The key to accurately measuring clearances with a feeler gauge is judging the amount of resistance when you drag the blade through the measured opening. The best way to learn what that resistance feels like is to practice with a micrometer. The setup for this practice is the same as for calibrating feeler gauges. Please review the previous screen if you have any questions. With the micrometer set up for the value noted on the blade, practice dragging it through the opening between the anvil and the spindle. So that you feel dragging resistance the same way every time, be sure to clean the blade before each use. Hold the blade near the tip. Hold the blade loosely and never force the blade through the opening. It's easy to damage the blades, in particular the thinner ones. To get a feeling for clearances that are too loose and too tight, also try the next smaller blade and the next larger blade. To read a feeler gauge, simply note the value that is engraved on the blade. Be sure to note the position of the decimal point when reading the value. Names of the vernier caliper's parts and understanding what they do will help you use it effectively. The parts of the vernier caliper are the points, jaws, main scale, vernier scale, tip, thumb rest or thumb lock, and the locking screw. Digital calipers have the same parts, except that the vernier scale is not used. There is no way to calibrate a simple vernier caliper such as this one. However, you can do a quick check before you make a measurement. Close the jaws all the way and make sure the zero mark on the vernier scale is exactly opposite the zero mark on the main scale. If it isn't, clean the jaws and try again. If the jaws are clean and the marks still don't line up, the instrument may be damaged. There are several types of vernier calipers. This module will cover the type most commonly used. This type of vernier caliper has two scales, main and vernier. The main scale is 20 centimeters long. Each centimeter is marked with a number on the main scale. The space between the numbers is divided into 10 spaces, each equal to 1 millimeter. A centimeter is equal to 10 millimeters, or 1/100th of a meter. The vernier scale has 20 spaces. The marking beside the scale tells you that the marks divide each millimeter on the main scale by 20. When you divide 1 millimeter by 20, you get 5/100ths of a millimeter, because that's what you get when you divide 1 millimeter into 20 equal parts. Each mark represents 5/100ths of a millimeter, with the first mark at 5/100ths of a millimeter and the second mark 10/100ths of a millimeter. To read the measurement of a vernier caliper, you simply read the value indicated on the main scale, read the value indicated on the vernier scale, and add the two values together for the total measurement. To read the value indicated on the main scale, note the point where the zero mark on the vernier scale points on the main scale. Make sure to use the zero and not the beginning of the jaws. In this example, it is more than 11 millimeters. To read the value indicated on the vernier scale, find the line on the vernier scale that lines up exactly with a line from the main scale. In this example, the line marked 6 or 6/10ths on the vernier scale is lined up precisely with a line on the main scale. Add the two together to come up with the total measurement, 11.6 millimeters. Let's try another example. In this case, the value indicated on the main scale is more than 5 millimeters. The mark on the vernier scale that lines up to the main scale is 1 or 1/10th. This gives us a total measurement of 5.1 millimeters. Knowing the names of the dial indicator's parts and understanding what they do will help you to use it effectively. The parts are the outer scale, moving needle, tracer pin, and inner scale. Digital dial indicators replace the needles with the digital readout and function buttons.
but still have a tracer pin.
Strictly speaking, you don't calibrate a dial indicator. What you do is set it up and, when you're ready, rotate the outer scale, like this, so that the needle points to 0.
On digital dial indicators, follow the same steps, but instead of turning the outer scale, reset the readout to 0.
The setup has two parts: preloading the tracer pin and finding the lowest point of measurement. Let's talk about preloading. It simply means that you start your measurement with the tracer pin already moved in about half of its travel. So, if you're using a 5 mm dial indicator, you preload to 2 or 3 mm on the inner scale. Preloading makes sure that the dial indicator will be able to measure travel in both directions. Tracer pin moves in and tracer pin moves out. Now, with the dial indicator properly positioned, and we'll talk more about positioning in the next section, rotate the part a few times to find the lowest measurement point. That'll be the point where the needle reverses from the counterclockwise to the clockwise direction. Now, turn the outer scale so that the needle points to 0 when it's at that point, and you're ready to take a measurement. In this example, we'll set up a dial indicator to measure runout. First, make sure the surface of the part you're measuring is clean. Then set up the dial indicator so the tracer pin is aligned with the expected movement of the part. In most cases, that means you'll position the pin perpendicular to the part's surface. Next, set the preload to about half the travel of the tracer pin. Then lock the indicator in place. Now, slowly turn the part to find the measurement low point.
On analog dial indicators, turn the outer scale on the dial indicator so the dial points to 0 when it's at the low point. On digital dial indicators, reset the readout to 0.
Now, turn the part at least 2 full revolutions as you observe the needle.
On analog dial indicators, read the maximum movement of the needle on the outer scale.
If the needle makes more than 1 full sweep, you'll have to add the reading on the inner scale to the outer scale value to get the total measurement.
On digital dial indicators, observe the measurement shown on the readout.
In this example, we'll set up a dial indicator to measure end play. Again, make sure the surface of the part you're measuring is clean. Set up the dial indicator so the tracer pin is aligned with the expected movement of the part. Next, set the preload to about half the travel of the tracer pin. Then lock the indicator in place. Now, move the part back and forth to find the measurement low point.
On analog dial indicators, turn the outer scale on the dial indicator so the dial points to 0 when it's at the low point. On digital dial indicators, reset the readout to 0.
Now, move the part through at least 2 full cycles back and forth as you observe the needle. Read the maximum movement of the needle on the outer scale. If the needle makes more than 1 full sweep, you'll have to add the reading on the inner scale to the outer scale value to get the total measurement.
On digital dial indicators, observe the measurement shown on the readout.
Each tick mark on the dial's outer scale is equal to 1/100th of a millimeter. Notice the scale reading in these examples: 5/100ths of a millimeter, 18/100ths of a millimeter, 54/100ths of a millimeter. Each full revolution around the outer scale is equal to 1 millimeter. The needle on the inner scale moves in proportion to the needle on the outer scale. The reading of the inner scale must be added to the reading of the outer scale to come up with the total measurement. Notice the scale readings in the following examples: 1.35 millimeters, 4.57 millimeters, 8.72 millimeters. Knowing the names of the micrometer's parts and understanding what they do will help you use it effectively. These parts are the anvil, spindle, thimble, ratchet knob, spindle lock, digital scale, sleeve, and frame. There are 2 ways to check the calibration of a micrometer. First, make sure the anvil and the spindle are clean.
Then screw in the thimble until the two surfaces touch. Don't forget to use the ratchet knob for the last few millimeters. After the click, the digital display should show all zeros, and the zero line on the thimble scale should be exactly aligned with the index line on the sleeve scale. A second way to check calibration is with a standard. A standard is a piece of metal that has been precisely machined to close tolerances. The piece will be marked with the dimension. When you measure the standard, the micrometer should display that dimension. Always hold the standard with your fingers on the plastic. If you touch the metal, the heat from your hand could cause the standard to expand. If the micrometer is out of calibration, calibrate it according to the manufacturer's instructions. You can hold a micrometer one of two ways. This is one way with your left hand on the center of the frame and your right hand turning the thimble and the ratchet knob. You can also cradle the micrometer in your right hand, like this, and use your thumb and forefinger to adjust the thimble. Make sure the instrument is clean before you start, and pay particular attention to the measuring surfaces. Screw out the thimble until there is an opening just large enough for the part you want to measure. We'll demonstrate with this thrust washer. Position the micrometer or the part so that the anvil touches the washer. Now use the ratchet knob to bring the spindle into contact with the other side of the washer. Once the ratchet knob clicks, apply the spindle lock. Separate the washer from the micrometer and read the measurement. We'll measure a piston skirt for our second example. This measurement requires a larger micrometer, but it works the same way. Again, make sure the instrument is clean, especially the measuring surfaces. Move the spindle until the opening is just large enough for the skirt. Position the micrometer near the bottom of the skirt. Refer to the appropriate service information to determine the exact location to place the micrometer. As you screw in the ratchet knob, keep a loose grip on the micrometer frame so that the measuring surfaces can self-align on the part. After the ratchet knob clicks, set the spindle lock. Separate the micrometer from the piston and read the measurement. Digital micrometers have a single digital readout that displays the measurement value. Buttons on the micrometer are used for various functions according to manufacturer's specifications. To read the measurement, simply look at the value in the readout display. There are some differences among analog micrometers in how the scales are arranged. The layout we will use is the one most commonly found on micrometers. It has 3 scales: main, thimble, and vernier. As the zero mark on the thimble comes around and gets closer to the index line, you'll see part of the next tick mark on the main scale. You do count the mark when the zero is at or below the index line. To read a micrometer, take the value of all 3 scales and add them together. Read the main scale first. The long tick marks are 1 millimeter. The short tick marks are a half millimeter. Take the reading where the thimble intersects the scale, counting the tick marks from left to right. As the zero mark on the thimble comes around and gets closer to the index line, you will see part of the next tick mark on the main scale. You do count the mark when the zero is at or below the index line. The thimble scale divides each half millimeter on the main scale into 50 parts. Therefore, the thimble scale has 50 tick marks. The reading is taken at the horizontal index line on the sleeve. Each tick mark on the thimble represents 1/100th of a millimeter. The scale reads from 0 to 49. 1 full revolution of the thimble will change the reading on the main scale by a half millimeter. 2 full revolutions will change the reading by 1 millimeter. If the tick mark on the thimble scale does not align precisely with the index line on the sleeve, read the value that is closest to and below the index line. The vernier scale divides each hundredth of a millimeter on the thimble scale into 10 parts, giving a reading in thousandths of a millimeter. Take the reading where a tick mark from the vernier scale most closely lines up with a tick mark on the thimble scale. This example illustrates how all three scales are added together to get the total measurement. Record each part of the measurement as you read it. The main scale, thimble scale, and vernier scale. Add all readings together to get the total measurement. The cylinder bore gauge is used to measure the internal diameter of cylinder bores and to check for out of round and taper. Knowing the names of the cylinder bore gauge's parts and understanding what they do will help you to use it effectively. The names of the parts are the dial indicator or digital readout, plunger, interchangeable rod, assortment of interchangeable rods, extension for interchangeable rods, assortment of washers for the interchangeable rods, and the handle. Digital cylinder bore gauges show the measured value in the readout display. It is a direct reading with no additional calculations needed to determine the final measurement. On analog cylinder bore gauges, some differences exist in how the scales of the dial indicators are arranged, depending on the gauge you are using.
It is essential that you know how to read the scales and differentiate between them. To use a cylinder bore gauge effectively, you need to know the precision the gauge is capable of measuring and how to read the scales of the indicator. The face of the dial will display the measurement range and degree of accuracy of the gauge. This gauge is capable of measuring to the nearest hundredth of a millimeter. Gauges that can measure to 1/100th of a millimeter typically have a range of 0 to 5 millimeters. Large numbers reading in one direction around the outer scale of the face, and smaller numbers reading in the opposite direction on the inner scale of the face. This allows the gauge to produce readings on both halves of the gauge face. Each tick mark on the outer scale is 1/100th of a millimeter. Each full revolution around the outer scale is equal to 1 millimeter. The inner scale is only used to preload the gauge before taking a measurement. This gauge is capable of measuring 1/1000th of a millimeter. Gauges that can measure to 1/1000th of a millimeter typically have a range of 0 to 1 millimeter and a split face, reading the same in each direction on the face. Always use the correct cylinder bore gauge for the application you are working with. The gauge we will cover in this module is capable of measuring to 1/1000th of a millimeter. The cylinder bore gauge has a special dial indicator. The face is split into left and right sides, with both sides going from 0 to 100. Each mark on the main scale equals 1/1000th of a millimeter, with each number representing 1/100th of a millimeter. When the needle points to 100, the value is 1/10th of a millimeter. The inner scale is divided into tenths of a millimeter. The needle moves 1/10th of a millimeter each time the main needle makes half of a revolution. One full revolution of the outer scale is equal to 2/10ths of a millimeter. The left side of the dial indicates values larger than the setup dimension. The right side of the dial indicates values smaller than the setup dimension. Note: allowable wear on cylinder bores is always less than 1/10th of a millimeter. For cylinder bore measurements, you will use the inner scale only for preloading, and the actual measurement should fall on the left side of the dial between 0 and 100. This example illustrates how to read the dial indicator. The standard dimension is 87 millimeters. The service limit is 87.07 millimeters.
This provides an allowable wear of 0.07 of a millimeter. This gauge has been set up for 87 millimeters. The dial was zeroed with the inner scale set to 0.5 millimeters. The needle is pointing to 40 on the left side of the scale, indicating that this bore is 0.04 of a millimeter larger than the standard. Begin the measurement by looking up the standard or new bore dimension in the service information. Use the smallest dimension given for the block you're working on. Write it down. Choose an appropriate size micrometer and set it to the standard or new bore dimension. Choose an interchangeable rod and washer, if needed, to set up the cylinder bore gauge. What you want is for the plunger to be slightly depressed when you place the gauge between the spindle and the anvil of the micrometer. It's best to set up the gauge so that the pointer is near the midpoint of the inner scale. That way you know you have sufficient preload. Turn the outer scale on the dial indicator so that the needle points to 0. Note the indication on the inner scale and write it down. Hold the bore gauge by the handle. Keep your hand relaxed. Don't grip it like a hammer. Gently place the gauge into the bore and keep the plunger and interchangeable rod parallel and at a right angle to the bore. Now, lower it to the depth where you want to measure. Once you have the gauge in position, slowly rock it side to side as you watch the dial indicator. You're looking for the point where you get the highest reading. The highest reading is the point of the most accurate measurement. Make your measurement smaller as you get close to seeing that reading. Note the reading and write it down. Now you can proceed one of two ways. You can put the bore gauge back into the micrometer and adjust the spindle until you get the same reading on the dial indicator that you did when it was in the bore. The micrometer scale will display the bore diameter. Or you can add the dial indicator reading to the bore dimension to get the bore diameter. The dial indicator reading reflects how much the cylinder bore has worn. For every cylinder bore, there is an X and Y axis. The X-axis goes across the engine, perpendicular to the crankshaft. The Y-axis runs parallel to the crankshaft. Take your measurements, 6 millimeters from the top of the cylinder, in the middle of the cylinder, and at 6 millimeters from the bottom of the cylinder. The difference between the X-axis value and the Y-axis value tells you the amount that the cylinder bore is out of round. The difference in the measurements you made at the top and bottom of the cylinder will give you the cylinder taper. A variety of telescoping gauges are used to measure the inner diameter and small bores. There are two main types of telescoping gauges: the split ball gauge and the snap gauge. All telescoping gauges, whether they are split ball or snap type, work roughly the same way. Carefully slide the tool into the bore, then tighten the tool so that it will hold the measurement when you pull it out of the bore. You can then use a micrometer to obtain the measurement of the bore.